Good morning, Physics 20. I hope you guys are having a good day today. Today, we are going to be looking at Newton's laws again. This time, we're going to be more focusing on Newton's first and third law. Now, the significance of that is what we've already done, Newton's second law. Now, these particular questions that you are going to be seeing, ladies and gentlemen, are going to be entirely based on theory questions. So, lessons learned on your assignment that is up and coming that you guys should be working on. Question at a time. See Google Classroom for details about essentially the link where you found this video. I'll be telling you what questions you need to do on the assignment. There's going to be a lot of theory questions on Newton's laws, and this is where you're going to come to find your theory questions and lessons learned on your unit test. This is where you will study for your theory questions. Sounds good? Cool beans. All right. So, ladies and gentlemen, are you guys ready to begin? You guys like the pun, right? Little meme. The cats are pretty cute. All right. So, ladies and gentlemen, Newton's laws, primarily focusing on the first and third. All right. So, ladies and gentlemen, Newton's second law, we've already done a whole 47-minute video on that. Once again, I'm sorry, my vector arrows turned into wonky W's. So, recall Newton's second law is our F net equals ma equation, or A equals F net over m. So we've already talked about that, and Newton's second law of motion states that an unbalanced force is going to cause a mass to accelerate. Sounds good? Cool beans. So the next law we're going to talk about, Newton's first law. Now, this is the law of inertia. So another name for that law. And it states that an object will remain at a constant velocity, including zero. Zero is a constant velocity, unless acted on by an unbalanced force. Another way that you could reword this is an object at rest has a tendency to stay at rest, or an object in motion has a tendency to stay in motion. So the idea of inertia is that an object is going to desire, forces don't actually have emotions. They are going to resist a change in motion. So an object is going to stay moving as it is unless it is going to have a force acted upon it. Okay? And the more mass, the more inertia an object has. So this is also related to braking, for example. So when you're going to be braking a vehicle, so now this is actually Newton's first and second law, is it's a lot harder to change the velocity or slow down a big vehicle than it is a small one. Not only because you're going to need a greater F net because of the larger mass, you're also fighting inertia as well. Okay? All right. So this is another reason why when you are going to be steering, so if you ever have a sharp curve, that's why it's easy on a road, a curve in the road, it's easier to drive a small car around a curve than it is a larger vehicle. So if you're going to be going around a curve in a smaller vehicle, it's easier to handle. When you go around a bigger or same curve with a bigger vehicle, you're going to want to slow down because that big vehicle is not going to want to go with the turn. Okay? It's just not as easy to do. The vehicle wants to keep going straight in either case, but because the truck is larger, it's going to have a harder time turning. So, for those of you fellow F-150 drivers, slow down on the curves. Four-wheel drive does not help your braking. Four-wheel drive helps you get unstuck. So if you're at a stoplight and it's icy, four-wheel drive helps you get going. Four-wheel drive reduces a little bit of the side shimmying on roads that are icy, but it doesn't help you stop. So don't drive like a schmuck just because you have four-wheel drive. Sounds good? No driving like a schmuck. All right. So let's look at another example of inertia here. This is a classic example. This is also why we have seatbelts. Well, one of the reasons. We spend a whole bunch of time talking about momentum and impulse in Physics 30, where we talk more about these vehicle safety features. So you're in a car, you slam on the brakes. Okay. And when you slam on the brakes, notice you are tossed forward and caught by your seatbelt, and you get kind of like gouged in the shoulder by your seatbelt. Well, the reason why that is because when you are driving in a car or a passenger in a car, you are also moving, and if you're on the highway, you're also going at 100 kilometers an hour, 110 kilometers an hour, assuming you're following the speed limit. No driving like schmucks. Okay, so if you're going 110 kilometers on the highway, on one of the divided highways, and you have to slam on the brakes because a deer runs out in front of you or something, you yourself, your carcass, is moving at 110 kilometers an hour. So that seatbelt is going to hold you back. The vehicle's stopping, but you're moving forward. So you need to make sure to wear your seatbelt. Okay? Because your body's going to want to keep moving. Okay. So that is a very classic example. So when you suddenly apply the brakes, your passenger's going to scoot forward a bit because of the inertia that you have. All right, so another lovely example that we have here is, as I mentioned earlier, driving in a curve. So if you're driving your car in this direction here, and then your car is going to curve, and if you do this a bit faster, you are going to have a tendency to lean. So as you curve, your passengers are going to lean a bit this way. The reason why is you have inertia that's going straight, and as you're driving around the corner, your body's going to want to go straight while the car is turning. So it feels kind of like you're leaning into the side of the car. Neat, eh? I think it's cool. Okay. So, ladies and gentlemen, next law of motion, Newton's third law. Okay. So, Newton's third law of motion states when an object exerts a force on a second object. Sorry, the dog is asking to come inside. I will be right back. Okay, guys? Let me pause the video here. Right, sorry, the dog was being a schmuck and barking her head off while outside and while asking to come in. All right. So for this Newton's third law, ladies and gentlemen, when an object will exert a force on a second object, that second object is going to exert an equal and opposite force on the first object. Okay? So, in other words, for every action, there's an equal but opposite reaction. Okay? Forces always, therefore, occur in pairs. Okay? So, this is the entire concept behind rocketry. So, or in this case, or when you release a balloon, I don't have a balloon. I actually went and looked around my house to see, do I have a balloon so I could release one on video? But sadly, I don't. So when you're going to release a balloon that you've blown up, you know how it flies around the room? Well, the reason that happens is that the air, as you are releasing the balloon, the air is going to be going out this way. The air leaving the balloon is the force. The balloon's leaving this way. The air is accelerating. You got a net force acting on that air. Well, the balloon is going to be going opposite directions. So as a force is being exerted, as the air is exerting a force this way, the balloon is going to experience a force this way. Okay? So what this means, the force of the air is going to equal the negative force on the balloon. Now, that negative is just telling us that it's in an opposite direction. Okay? So the magnitude is the same, but the direction is opposite. Okay? Okay. So, I nearly said any questions, ladies and gentlemen, but I'm on YouTube right now. can't exactly answer your questions. As you're watching, going to be watching this in the future from where I am now. All right, so ladies and gentlemen, our next piece is we are going to be looking at the recoil of a firearm. So it is the exact same concept. Here we've got a cannon. For those of you who have ever fired a rifle before, you will realize that the larger the caliber of the rifle, the more recoil there is going to be. So if you're going to be plinking with a little .22, then there's virtually no recoil, okay? Because the force necessary to propel the bullet forward is significantly less. So therefore, the opposite force, the force that the bullet applies to the firearm, and then therefore you, is significantly less. Whereas if you're going to be shooting a very large rifle, like a 45-70, for example, the recoil is huge because in order to move the larger bullet forward with that level of acceleration, you need a larger net force. So that is where the recoil of firearms comes from. All right. So, ladies and gentlemen, with this, if Newton's law states that there are equal forces acting on each mass when you push an object, this is why the bullet is going to accelerate a lot more than the gun is going to accelerate backwards. Why is that? The mass. The mass of a bullet is tiny. Whereas the mass, so you can measure it in grams, whereas the mass of the gun will be measured in pounds or kilograms. I think my hunting rifle, by the time I put the scope on it, something like 10 pounds. So versus the bullet, which would be like, I don't know, maybe a gram, something like that. They're tiny. So the force necessary to get the acceleration of the bullet is going to be less. The force is the same, but the bullet's going to have much higher acceleration because the mass is significantly larger of the gun itself. The same concept of why if a person on a skateboard or a wheelie chair or something, it pushes on the wall, the person is going to accelerate, but the wall is going to stay where it is. Why is that? Well, like with this diagram that we have here, you can see that the person is pushing on the wall. So the wall is experiencing a force to the right here, and the person is experiencing a force to the left. However, when you push on the wall, does the wall move? No. The wall doesn't accelerate because there's not enough force to move the wall. Whereas the force that the wall is applying to the person is going to move you on the skateboard because that is sufficient force to overcome friction there. Okay, so ladies and gentlemen, less than subtle hint, you're going to see a question about this on your assignment. Okay, so the smaller mass is going to experience a greater acceleration in this case because when you look at your equation F net over m, okay, if you have your mass here as larger, this number is going to be smaller if this number is the same. Okay, so when we are going to be looking at it from this angle, okay, where we're changing the mass, okay, if our F net is going to be constant the same way that F net is constant in the scenario of pushing on the wall with a skateboard, each the wall and the person experience the same F net, opposite directions, but same magnitude. We can then write our equation as our acceleration is proportionate to 1 over m. So this is the inverse. These are called inversely proportionate. Inversely. I don't know if there's an E in there or not. Sorry, my spelling stinks. Stinks, I say. Aren't you glad I don't teach you English? I'm glad I don't teach English too. That'd be scary. Okay. So they are inversely proportionate. There we go. So when you are going to increase the mass, the acceleration is going to decrease if F net is the same. Cool beans? Cool beans. So lesson settlement, you do have an assignment question based on that concept. Sounds good? Cool. So ladies and gentlemen, we've got some practice problems there from your workbook for you guys to take a shot at. And then we've got these 3 questions here, which are more practice problems for you to do. And the answers are on the same page in your notes. All right, so give the practice problems a try. I hope you guys have a good rest of your day. No fires, injuries, or explosions, and avoid rampaging viruses. All right, now I need to figure out how to turn this off again. We're going. All right, talk to you guys later. Bye.